Welcome to Calculus Lecture 6. This is Derivation Rules. Now that we've seen how derivatives are determined algebraically using limits, we notice that certain patterns emerge. We can summarize these patterns using the following derivation rules. So to start off, we've got the derivative of a constant. If c is a constant, some real number, then the derivative with respect to x, or any other variable for that matter, of a constant is 0. Okay, and this is because the slope of a constant function is 0, right? So if we were to plot a constant function like y equals 5, we see that slope is not changing. y2 is equal to y1 over any distance of x. So slope is equal to 0, and therefore the derivative is equal to 0. Okay, we've got some examples here. So suppose we had something like y equals 7, its derivative is 0. Even if you had a function where f of x is equal to 0 already, its derivative remains 0. So 0 is just a real number, it's just a constant, its derivative will also be 0. And if you had something of the form, say k pi squared, remember these are all constants. K has to be defined, right? If it's defined as a constant, pi is also just a constant. It's an irrational number, and we write it sometimes as if it were a variable, but as it is in fact a constant, its derivative is also going to be 0. Okay, so the derivative of a constant is 0. Next up, the power rule. This is probably one of the most common rules and one of the most useful rules. So this says that if n is a rational number and the function f of x is equal to x raised to the n power is differentiable, that is, we can actually take the derivative of it, then the derivative with respect to x of x raised to the n power is n times x raised to the n minus 1. So that original power comes down in front of x as a coefficient, and then from that original power you subtract a 1. And that's what you're left with. Okay, so the original power is now here as a coefficient. The new power is going to be 1 less than whatever you started with. Okay, that's exactly what we have said here. So for example, let's suppose we had f of x is equal to x to the third power. That 3 is going to come down and multiply by x, and then in the exponent over here, we're going to subtract a 1. So that's going to be 3 minus 1 becomes x squared. Okay, suppose you had something like g of x is equal to the cube root of x. Well, we know that we can rewrite cube roots, or any roots for that matter, as powers. Okay, so the cube root of x is the same thing as x raised to the 1/3 power. We take that derivative of x to the 1/3 power. That 1/3 comes down as a coefficient. From that, you subtract a 1. Now 1/3 minus a 1, or we can rewrite that as 3 over 3. 1 minus 3 is going to be negative 2. And we're going to maintain that same denominator. So negative 2 over 3. Okay, so the power rule works just as fine for fractions. Any sort of rational numbers. Okay, and then last example, 1 over x squared, we can rewrite this as x raised to the negative 2 power. And we can go ahead and we apply the same rule. Negative 2 comes down, becomes a coefficient of x. From negative 2, subtract 1. Negative 2 minus 1 is going to give you negative 3. Now, we have a special case here when n is equal to 1. Okay, so when that power of x is actually equal to 1, well, it looks like just x, right? X raised to the first power is just x. So the derivative of this is just 1. Okay, and the reason this works is because x raised to the first power, you use the power rule, you bring the 1 down. 1 becomes the coefficient of x. From that 1 that was up there, we subtract 1. So you have 1 times x raised to 0 power. And if you remember from before, anything raised to 0 power, except for 0, is 1. Okay, 0 raised to 0 power is indeterminate, right? But everything else goes to 1, including this x. So 1 times 1 is 1. Now, I wouldn't think through this entire process every single time you have to take the derivative of x. I would just remember that the derivative of x by itself is just going to become 1. And if you had some sort of constant in front of it, if we take the derivative of this, we're going to see in a second that's just going to, that constant is the only thing that's going to become preserved. And we'll see in a second why that's the case. Okay? That is the case, in fact, because of what's called the constant multiple rule. So if f is a differentiable function, and c is a real number, then c times f is also differentiable. And it follows the following rule. The derivative with respect to x of c times f of x is the same thing as c times the derivative of f of x. So you can just bring that c right out of there and just worry about taking the derivative of f and then just multiply again that c at the very end. Okay? So that constant comes out in front of the function, and you can derive f of x first before multiplying c. So in that example I had just given, so if we said something like we had 5x to the first power, we're just really doing this. We're just doing 5 times the derivative of x, which we just saw was 1. So 5 times 1 is 5. Okay, let's look at some more examples of these. Let's suppose we had y is equal to 5x cubed. The derivative with respect to x of 5x cubed, well, the 5 comes outside. The x cubed remains, and for this part we use the power rule. That 3 comes down, and then we subtract a 1 from the 3, right? So we get 5 times 3x squared. You can put that together as 15x squared. Another example, y is equal to 2 divided by x. We can rewrite that as 2 times x to the negative 1 power. That 2 comes outside. We worry about taking the derivative with respect to x of x raised to the negative 1 power. From here, we use the power rule. The negative 1 comes down. From that negative 1, we subtract a 1 over here. We get x to the negative 2. So we will get negative 2 x to the negative 2. Alright, so that's the constant multiple rule. Now let's talk about the sum and difference rules. So sum and difference of two differentiable functions, f and g, is itself differentiable, as in we can take its derivative. Okay, and it just follows this sort of rule right here. So very similar to limits, the derivative of the sum is equal to the sum of derivatives. So we can just individually derive f of x, we can individually derive g of x, and then we can just add them back together. And that's what the derivative of f of x plus g of x is. And the same pattern holds for differences. So the derivative with respect to x, the difference of f of x and g of x is just the difference of their derivatives. Go ahead and derive them individually, and then just subtract them at the end. Okay. So let's see some examples of how that might work. So if we had a polynomial here, like y is equal to x cubed minus 4x plus 5, all we have to think about is the derivative of each term individually. We apply a power rule to the first one. 3 comes down as a coefficient. Subtract 1 from that 3. We're going to get 3x squared. This is negative 4x to the first power. And just like we saw before, the derivative of x to the first power is just 1. And by the constant multiplier rule, we just bring that negative 4 back. So negative 4 times 1. And for the last one, for that 5, that's just a constant. By our very first rule, the derivative of a constant is 0. So we will be left with just 3x squared minus 4. Okay, and we just bring them together as an addition or a subtraction. For the next example, we've got y is equal to negative 1/2 x to the 4th power plus 3x cubed minus 2x. We go ahead again, derive each term individually, and then we're just going to put together a linear combination of them all. Okay, so for the first case, let's hold off on that negative 1/2 as a constant multiplier. Bring down that 4 as a coefficient. Subtract 1 from the 4, we get 3. Okay, so now we have negative 1/2 times 4x cubed. Similar deal for the 3x cubed over here. This 3 is just going to sit aside for a second. The 3 as the exponent is going to come down and multiply as a coefficient. And from that, again, from that 3 as an exponent, we're going to subtract 1. And that's going to give us 2 as an exponent. And for that very last term, negative 2x, well, again, x to the 1 is just 1. When we take a derivative of it, that constant multiple just stays. Okay, so it's just negative 2 times 1. And then we just put these all together. This is a positive term, so we're just going to put a plus sign between those two. Go ahead and simplify. Negative 1/2 times 4, negative 2x cubed for our first term. 3 times 3 will give us a 9x squared over here. And then we have a negative 2 at the very end. Okay, so that's the sum and difference rule. Pretty straightforward, also very useful, very powerful. And last thing I want to talk about is the derivatives of exponential functions. Now, an exponential function is not just something with an exponent. It's when the exponent itself is the variable, right? It's not a variable raised to some constant. It's typically a constant. It could also be a variable raised to a variable power. Okay, so for any positive real number a, if f of x is defined as a raised to the x power, in this case a constant, then the derivative with respect to x of a to the x power is going to be equal to a to the x times the natural log of a. Okay, so natural log is being added onto it. So for example, if we had f of x is equal to 2 raised to the x power, the derivative is going to be 2 raised to the x power times that natural log term. So every time we take the derivative, this natural log term is going to be added. Same deal here. P of t is equal to 10 raised to the t power. The derivative of that is going to be 10 raised to the t power times natural log of 10. Okay. Now we have a special case when that real number is e, Euler's number. Okay. If we were to take the derivative of this with respect to x, well, we're going to get e to the x times the natural log of e. But the natural log of e is itself simply 1. So we're left with just e to the x. Okay, so this is a very special case because e to the x is its own derivative. When you take the derivative of e to the x, nothing happens. It remains the same. Okay, so it's a very special case where the function e to the x, the slope of the tangent lines anywhere along this function are defined by the same exact function. Okay, that's a very unique case. So in practice, if you had some sort of multiplier in front of e to the x, well, that multiplier would come out. So if you had 3 e to the x, we would separate this, take the derivative of e to the x, but that's just e to the x. And that 3 comes back and multiplies again. So even with a constant in front of it, that function's derivative is the same as the original function itself. Okay, now you could have e to the x in combination with something like x squared, and by the sum rule of derivatives, you're going to take the derivative of the first term, and then the derivative of the second term. By power rule, the derivative of the first one is 2x, the second one will remain e to the x. All right. So this was just a quick look at some differentiation rules. I hope this helped as an introduction. So once you have these rules, we don't have to use algebraic limit definitions anymore to evaluate derivatives, and this is going to save us a lot of time from here on out in evaluating derivatives. All right, thank you for watching. If you enjoyed this video, please like the video and subscribe to the channel for more videos. Thank you.